In this session, we're going to take a look at the difference between latches and flip-flops. Last time we looked at three latches, the NAND latch, the NOR latch, and the D latch. The NAND latch and the NOR latch are our two basic latches, and both of them are called set-reset latches. They both operate a little bit differently, but perform the same basic function. So if we look at the NAND latch to start with, we can see that it has active low inputs, and we know that because of the bar on top. And here we have active high inputs. The operation is pretty much the same though. We're looking for a set, which is when we have an active set and an inactive reset. So here we're going to have an active set here, an inactive reset here, which gives us a set. And in our NOR latch, we're down here. Set is active, reset is inactive, giving us our set. In order to get a reset, we need the opposite condition where we have reset active and set inactive, reset active here and set inactive, and a hold when both are inactive. So here we have them both inactive high, here we have them both inactive low. The problem with our set-reset latches is this unstable state. So when both of the inputs happen to go active at the same time, the device goes into a state where we can't predict how it's going to behave. And that's what the D latch did for us. It cleaned that up. So what we have here as inputs are an enable, which is like an on-off switch, and our bit stream, or our data coming in. Now remember, this was also called a transparent latch, which means when enable is high, we're going to see on the output what's coming in the input. So we can see here when enable is low, we're holding the value stored in the latch. When enable is high, the output is the same as the input. The D latch is considered a gated device. What that means is because of this enable control, we have the ability to turn it on and off. You'll also hear the term asynchronous associated with this. Asynchronous means there's no clock that's controlling it, so it's not synchronized to a clock pulse. So if we introduce a clock instead of an enable pulse, we have what's called a clock device. And you can see a clock pulse here. We have a 50% duty cycle, and we basically have a pulse of on and off logic levels. Given our input A and B to this device, we're going to generate an output Q. The little triangle that you can see in the symbol here means that it's a clock device, and anytime you see that, you can start by drawing a regular clock pulse. Now when we have a clock device, it can either sample on the rising edge of the clock or on the falling edge, but what's going to happen is, depending on the edge, we're only going to sample, like the sample and hold we had with the enable pulse, we're only going to sample here or here. So this particular device tells us, because there's no bubble on this clock input, that we're going to sample on the rising edges. If there was a bubble there, we'd sample on the falling edges. So what we would normally do is come along on our timing diagram and mark in all of those rising edges. What we're going to do is sample our device just at that point. So we're going to take a sample of A and B here, 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 and here. Depending on what they are and what this device happens to be, we're going to define what Q is. A flip-flop is a storage device like a latch, except it's a synchronous device. That means that it's controlled by a clock. We can see that clock here in the internals diagram, and we can see it here in the symbol. Notice the triangle in the symbol as well, indicating it's a clocked device. In this particular case, we can see the bubble on that input, which means we're going to be looking at the falling edge on this device. Let's take a look inside. We can see here a typical NAND latch. So you should be recognizing the cross-coupling that we see here. And we should also recognize that we need an active low in order to set or reset the device. Q is our output. If we get a set, Q is going to go high. If we get a reset, Q is going to go low. So this circuit inside the red box is designed to ensure that we get that active low we require to set or reset the NAND latch. So this top one is going to give us that low when set is high and we get the appropriate signal on our clock. The one down here is going to give us the active low when reset is high at the same time as we get the appropriate signal on our clock. This circuit out front is called an edge detection circuit, and what it's going to do is take that regular clock pulse and give us a very, very short pulse on the falling edge of that pulse. So let's take a look at how that works. So here's that edge detection circuit that was inside the flip-flop. Here we have our regular clock pulse, so we have a square wave coming in here. And it gets passed through an inverter, and both the normal clock and the inverted clock are fed into a NOR gate. Now we know that NOR gate is going to give us an active low whenever either clock is high or what I've labeled as clock as not clock is high. But that doesn't seem like that would ever happen because we know that these 2 points are always going to be opposite. But what we have to remember is the propagation delay that occurs between the input of a gate and the output of a gate. So that means down here when clock changes, so here's our clock pulse, it goes low, that as it changes there's going to be a little bit of a delay because of this inverter before what I've called not clock goes high. So what we're interested in is this little period of time right here. If we think about our NOR gate, we know because of De Morgan that we can change the gate, we can change the state of each input, and we can change the state of the output, and it's going to behave the same way. So if we look at this, we know the output's going to be high when the 2 inputs are low. That happens to be the case we have right here. So both of them go low, our output's going to go high, so for the length of that propagation delay, we get that tiny little pulse I've called clock prime, which is all we need in order to trigger our flip-flop. So we've looked at set-reset latches. Now let's look at a set-reset flip-flop. We can see the symbol for it here, and we can see its truth table here. So you'll notice in the truth table we have a column that indicates the clock now, and that clock is shown with a down arrow, which tells us we're going to be looking for a falling edge device. We can also see that in our symbol, this little bubble out in front of the clock tells us that it's a falling edge. So the first thing we're going to do when we're working with timing diagrams is go in and we're going to mark those falling edges right on our timing diagram. What's going to happen with a flip-flop, and this is the main difference between a flip-flop and a latch, is that we're going to sample only at the clock. So what do we sample? Well, we know how a set-reset latch works, and we know that if we get a set, that Q is going to go high. So we can see here we get a set, Q goes high. We get a reset, Q goes low. Both inputs are inactive. We hold what value it has. When both of them go active, we still get that instability. So it doesn't matter whether it's a set-reset latch or flip-flop, we don't want our inputs to go active at the same time. So let's look at our waveforms now. We can see Q is starting low, and we can continue that right over till our first sample point. At that first sample point, we have set being high, reset being low. So set is high, reset is low, and we're on the clock edge. What's going to happen? Q is going to set. So we can mark that in, and it's going to stay in that state till the next falling edge. At this falling edge, S is low, R is low, so we're in our hold state. We're on the clock edge. What's going to happen? Q holds. So we're going to hold that high through to the next sample point. At this point, set is low, reset is high, so we have this state right here. Q is going to reset, so it's going to drop back to 0. At this point, set is low, reset is low. We're in our active or hold, our inactive or hold state, so we're going to hold that low. Then we come over to our next sample point. We have a low and a low, gives us another hold. And finally, we have a low and a low, which gives us another hold. So you can see that we lost what appeared to be some of these pulses. So we had a set here that we missed, a reset that we missed, because all we're doing is taking a look at the falling edge of the device. So the clock becomes pretty important when we're starting to talk about storage, because you can see that if it's not fast enough, we're going to miss some data. So in the next video, we're going to take a look at some of the other kinds of flip-flops. We're also going to talk about how we can prevent this instability from occurring.